In the last video I showed how to remove outliers from a dataset using the IQR method. In this video I want to talk a little bit more in depth about outliers and some other methods of outlier detection and removal. I'll go over 3 methods of trimming outliers from datasets to get more accurate means: the trim mean method, the standard z-score method, and the modified z-score method. Hello everyone, and welcome to the Engineering Toolbox channel, where I give you the tools you need to solve real-world engineering problems. So just like in the last video, I want to preface this with saying values determined as outliers aren't always something that should be removed. In fact, pretty much the opposite. This is very important to understand. Anyone with a good understanding of stats that's watching this video is probably yelling at their screen already, but hopefully I'm able to explain my case. Typically in statistics, we're told that outliers should not be removed unless they can be proven to be erroneous data points. These are things that are either not possible, like an adult weighing 12 pounds or something like that, or we can gather at least anecdotal evidence to prove that the data point is invalid. And this totally makes sense. However, from an engineering perspective, we're often trying to act on these statistics with limited data, time, or ability to set up controlled experiments. So if 9 out of 10 data points suggest one thing and the last looks to be an outlier, I'm going to assume that's a special case and act on the 90%. But just remember that by removing outliers from a dataset, we're making an assumption, and it's not necessarily correct. As you'll see in this video, there are different ways of determining outliers. That right there shows us that outliers are somewhat loosely defined. The method used to determine outliers directly affects what is classified as one. Each dataset and scenario is different, and without understanding the method used to determine outliers, what we plan to do with them, and having an overall conceptual understanding of the data itself, we can end up making incorrect assumptions. We should always ask ourselves what the goal is and be careful not to introduce bias by picking a certain method or just removing outliers just because it gives us the numbers we want. By the way, if there's any statisticians out there, I'd love to get your input on this. Anyways, let's dive in. Before we do this in Excel, let's quick run through each method. First is the trimmed mean method. This is not a method for detecting outliers, but it is one way of removing the potential outlier values in order to give us a potentially more accurate mean. It's very important to note that this method could very easily remove non-outlier values. It works by taking a certain number of values or a certain percent of the total count and removes them from the mean equation. In this example, the top 3 and bottom 3 values are being removed. This method does not work well for small data sets, but it does work well on skewed or fat-tailed distributions. The assumption we're making here is that the data left after trimming will be more normally distributed and more useful approximation of the mean. Next, the standard z-score method is a common way to detect outliers in large, normally distributed data sets. It works by calculating a mean and standard deviation for the entire data set, then calculating a z-score from each data point. Then comparing those z-scores to a certain threshold, oftentimes 3, 2.5, or 2 standard deviations from the mean, can be considered outliers. You can start to see how outlier detection can be pretty dicey. This method will not work with small sample sizes, definitely not under around 12, because the max standard z-score for that sample size is around like 3, and it gets even smaller as the sample size gets smaller. Last is the modified z-score, which is very robust because it uses median values to calculate a modified z-score value. For that, we use a formula where we need to find the MAD, or median absolute deviation. Now, it's pretty hard to explain this one visually, but I'll try to explain it more when we get into Excel. Just for comparison, let's look at an example. Here are the resulting means after removing the outliers each method detected. You can see that the values vary depending on the method used. You may have also noticed that essentially what's happening when we remove outliers is the mean of the remaining values move closer to the original median. So you might ask, why not just use the median in the first place? Depending on what you're trying to achieve, this is certainly an option. We need to ask ourselves again, what is the goal? Is it to approximate the normal distribution of the data, or just to understand where the central tendency is? If you're just trying to understand the central tendency where 50% of the values are above and 50% are below, then using the median is obviously the way to go. Let's look at some simple examples where we might want to remove outliers to get more representative means. If we're trying to understand the distribution and central tendency of a univariate dataset, or one variable, we might want to detect and remove outliers to gain a more realistic understanding of the distribution. In this example, we can see that the mean is very different depending on the inclusion of the outliers. If my job were to create a model to describe the interaction between 2 variables, like in this regression analysis, I would more than likely exclude these outliers because the resulting regression line does not fit the majority of the data points. Again, this is making a huge assumption that the data points aren't actually representative of the interaction. Even though we may choose to exclude the outliers, we should probably follow up this analysis by implementing more controls of the process. And that brings me to my final very important note. As engineers, we should always ask the question, why are there outliers in the first place? An outlier, or just the fact that there are outliers, can tell us a lot about the underlying process or the method of measurement. We should always try to investigate outliers and try to understand why they even exist. Oftentimes there's a ton of value in this investigation. Now you might find that there was just a simple error, or you might find that there is something fundamentally wrong with the process you're measuring. The cool thing about being an engineer is usually we aren't trying to simply understand data just for the sake of understanding it, but actually understand the data so we can change the underlying process that is driving it. That's what makes outlier detection so valuable. Alright, I admit I was all over the place in this one, probably because the topic of outliers can be so nebulous, and it's dependent on the situation and the outcomes we're looking for. I felt like I was talking in circles at times, but sometimes that's just the way my mind works. Now that we hopefully have a better understanding of outliers, why detecting them is important, and why we might want to remove them, I'll go over how we can actually do this using Excel in the next video. Anyway, I hope you found this video valuable, and if not, at least interesting or entertaining. If you did, make sure to like and subscribe to get my weekly videos. If you have any questions or there's anything I can go into more depth on, make sure to let me know, and maybe if you're lucky, I'll make a video about it. And as always, thank you so much for watching.